so I know it goes from 40 meters per second to negative 10 meters per second in 10 seconds along a straight line. So that was 40 to 20, negative 20. So initial velocity, 40 meters per second. Final velocity, negative 20 meters per second. Time, 10 seconds. And acceleration is constant. Initial position, so we know x of I, 50 meters. So from a graph point of view, if I have a velocity time graph, what's the acceleration?
And probably it was -6, right?
Okay,
constant.
so how would that show up in a velocity time graph?
The slope is -6. The slope would be -6.
Yeah. So I'm starting out at 40. I end up at negative 20 in 10 seconds here. Slope, -6. So because the acceleration is uniform and the acceleration is slope, the slope is uniform. In other words, the slope is constant. The acceleration graph, well, as been, uniform means constant, and has been established, -6 meters per second squared. Position, on the other hand, I start out at much faster speed and then I start slowing down. At some point, I stop and turn around. So what's the relationship between velocity time and position time? That's right. Oh, they corrected that. Oh well. So if I have position versus time, what's the relationship between this and this?
When the slope is, or when that y is positive on the velocity formula, the slope is positive
Okay,
on the,
so this is the slope of that.
yeah.
So I start out at a steep slope and my slope slowly or steadily gets smaller until my slope is 0 here. So at that time, which is, I guess, 6 2/3 seconds. So if that's 10, that's 6 2/3, that's 3 1/3. That's when it peaks. I start out at 50. And where do I end up? So what's my final position? So how would I find the displacement?
Okay, formula.
Yeah. Yes. Displacement is equal to the average velocity times time. So that's 40 plus -20 divided by 2 times 10. That's 20, so 100. Plus -20 is 10. That is 20 divided by 2 is 10. Yeah. So that's 50. Well, that's 100. It's going to end there. It starts here. It's going to peak at this point. Something like that. My slope starts out steep. It becomes less and less steep. At this point, it's 0. Then my slope becomes negative. My slope here is negative the entire time. thus negative the entire time. And then average acceleration. A more interesting question for the entire 17 seconds. The part that I apparently did not tell you is that at this point it travels at a constant velocity for the rest of it. So acceleration becomes 0. Obviously I can't penalize you for that. But how would you find average acceleration if acceleration is not constant?
Would it be the same way you find average velocity?
It depends on what you mean by that.
Acceleration at the beginning and then final acceleration divided by 2.
Oh, that only works if the jerk is constant.
Okay.
And jerk is not constant here. Well, not constant in the problem in my head. I guess it is constant there.
I just had a question. Can I grab my paper to take notes for it?
Sure. All right, so how do you find average velocity?
Delta S over delta T.
Pardon?
Delta S over delta T.
Yeah. It's the change in position over change in time. How would you find average acceleration?
Change in velocity over change in time?
Yeah. Now, in this particular case, the way the problem was worded, there was only 10 seconds of it. But if it cruised at negative 6 meters per second for 7 more seconds, then my average acceleration would be, well, I go from 40 to negative 20. So my change in velocity is negative 60 divided by 17 seconds. That's meters per second over seconds. Or in the problem that I gave you, it would be divided by 10, or negative 6 meters per second squared. Average velocity is change in position over change in time. So several ways of doing it. At this point, we know it starts at 50, it ends at 100, so the change in position is 50 meters, positive 50 meters divided by 10. Or, since acceleration is constant, my average velocity is just the average of my initial and final, so which is the sum divided by 2. And the distance traveled, well, it's traveling in a positive direction for this bit. It travels in the negative direction for this bit. So the question is, how far did it travel here? How far did it travel there? And you add it. So if I have velocity time, how would I find position? Or displacement, actually. Pretty sure I've done videos on this, you should have watched it by now. So if I'm going in that direction, I'm doing slope. So if I have position time or displacement time, I would do the slope. If I have velocity time, I do the slope to get acceleration. Suppose I'm going the other direction.
Output?
Excuse me?
Output of the graph? Or
What do you mean output?
like the Y, what's the data in the group?
Probably, I'm going to say no, if I'm interpreting your comment correctly. If you travel, this is velocity time. If you travel at a constant velocity of 50 meters per second for 10 seconds, what is your displacement?
500 meters.
One more time?
500 meters.
Yes. How'd you get that?
The area under the graph.
Yes. Or multiply the velocity times time, but it's the area underneath. So the displacement is the area under velocity versus time. So if I do the area here, that's gonna give me the change in velocity. Doesn't get me the velocity, just the change. And if I do the area under here, it gets me the change in position. So how do I find the area of a triangle?
1/2 base times height.
Yep. 1/2 times base, well, I've already established this is 6.67, or repeating, so 6.6666. Or make it less demonic, 6.6 repeating. Times the height, 40. This, 1/2 times 3.3, repeating, times the height there. Now, if I was trying to find displacement, I put the negative in there, this will end up with a negative value, this will be a positive value. If I'm looking for distance, this is a positive value. Doing the fancy math here, this is 30, this is a displacement of negative 33.3 meters, or a distance of positive 33.3 meters. And .3 meters. So my displacement, 133.3 meters plus negative 33.3 meters, gets me 100 meters, which is what we figured out before. Or from a distance, that plus that gets 166.6 repeating.
Dr. Fox, what does it say by the delta x velocity, right below the acceleration? What does that
Here?
say? Yeah, what does that say?
Area under velocity versus time. There is a mistake up here. Where was that? Yeah, where's, anyone notice the mistake?
You said it was missing a what?
There's a mistake, my position time graph is off. Based on my calculations, what is 100 meters? What did I solve for over there?
The displacement?
Yes. What is this a graph of?
Oh, position.
It's position graph. My displacement's 100 meters. So I end up at 150. I'm still peaking there. That peak would be at whatever 50 plus 133.3 is. 183.3. Right. I think I've hit pretty much all the questions.
So on the it asks for a change of position and displacement, but isn't delta position, isn't that what displacement is?
Yes,
So it'd be the same answer?
yes.
Okay.
I'm always surprised at the number of people who do not recognize that displacement and change of position are the same thing. Other questions?
For number 3, were you supposed to take the derivative of that equation to find the velocity and acceleration?
No. If you wanted to do it, fine, but you don't have to. All right, so I know, I'll do it over here. What if I put this thing back to my office? I know that the change in position is equal to VIT plus 1/2 AT squared. That. One of the K formulas, acceleration is constant. Change in S, or change in position, is just S final minus S initial, which is equal to VIT plus 1/2 AT squared. In other words, my final position, or my position, is equal to my initial position plus VIT plus 1/2 AT squared. So if I can express my position in some form like this, in a quadratic form, then, well, acceleration would have to be constant. Now, if you had calculus, to do the second derivative, you'll see acceleration is constant. But the equation I gave you was 3t squared negative 45t and 162. So that's my initial position. That's my initial velocity. That's half my acceleration. So that gets you problem A. And then the rest of it are just take formula applications.
I think it was C on number 3. It was saying what's the velocity if once it hits the ground and then 10 seconds later. So that just seems like it should be 0.
Average velocity V. No, so if I plotted velocity versus time, it starts out at negative 45 and then accelerates at positive 3 meters per second per second. So in essence, it's got a positive acceleration, positive 6. So at, was it 7.5 seconds? Yeah. At 7.5 seconds, it stops and turns around. So the question C of average velocity between the time it stopped and 10 seconds after it has stopped, I'm asking for the average velocity in this region here. It's not stopping and staying stop. Because if it did, acceleration is not constant anymore, and this equation no longer applies. Other questions?
About for number 7, when we were looking at that graph with the slope. So I was a little confused about that because I think when we were doing that type of problem on Thursday, you were saying the acceleration is going to be positive, or excuse me, negative when it's going, first time, but then when it turns around and comes back, it'll be when it's going across the friction, it'll be positive. You know what I'm saying?
Right. So in the friction, in that case, Any questions on this before I erase it? So if I say the positive is to the right, and this box is moving that way, if I've got a friction area right here, the force is acting on it, there's weight acting down, there's what's called normal force acting up. This is in chapter 4. It's basically the force that the floor exerts on it to keep it from falling. And then friction's trying to slow it down, so friction's acting this way. So in this case, because the box is moving in that direction, friction's acting opposite the direction of movement, and that is the negative direction.
And is that still the case even though it's on a ramp?
So if it's on a ramp, so in this case right here, frictionless level surface, trying to see where I mentioned friction. Box slides down the ramp, oh, with some friction, all right. So, as it's sliding down the ramp, I think it's built into the problem, the fact that the box makes it all the way down to the ramp and hits the opposite wall and then comes back. So while it's going down the ramp, because I have it starting at rest, starting from rest. If the friction were enough for the net force to be in that direction, then it would not be sliding down the ramp. And so just from the fact that I say it's sliding down the ramp implies that the force in that direction is greater than the force in that direction. So it'd still be it would be positive acceleration there. As it goes, so that's when the box starts out. At the end of it, when it's going this way, that there is this net force acting down the ramp. Because if the ramp were frictionless, it would still slow down. And there's also friction acting back that way. So in both cases, acceleration would be positive.
I have a question not about this.